In 1854, a German mathematician named Bernhard Riemann invented a new kind of geometry: curved spaces, abstract, beautiful, completely useless. 60 years later, Albert Einstein needed a way to describe how mass bends the fabric of spacetime. He found Riemann's geometry waiting for him, like it had been placed there. This isn't a one-time coincidence. It keeps happening. Mathematicians invent tools for purely abstract reasons with zero connection to the physical world, and then, decades or centuries later, physicists discover those tools describe reality perfectly. A Nobel laureate called this unreasonable. Einstein called it a miracle. And the greatest logician of the 20th century believed it pointed toward God. In 1960, the physicist Eugene Wigner published one of the most cited papers in the philosophy of science. Its title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner's observation was simple but profound. Mathematics is a product of human imagination. We invent it. We play with abstract patterns and structures for their own sake. Nobody tells mathematicians to solve the problems of physics. They're pursuing beauty, elegance, internal consistency. And yet, this purely abstract activity produces the exact tools that physics needs. Wigner wrote, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve." This isn't a religious claim. It's a scientific observation from a Nobel Prize-winning physicist, and it raises a question that science alone cannot answer. Consider 3 cases. First, complex numbers. In the 1500s, mathematicians invented numbers involving the square root of -1. There is no physical quantity that is the square root of -1. These numbers were invented to solve cubic equations, a purely abstract exercise. 300 years later, physicists discovered that quantum mechanics, the most precise theory in the history of science, cannot be formulated without complex numbers. The behavior of every atom in the universe is described by mathematics that was invented to solve a puzzle that had nothing to do with atoms. Second, Riemannian geometry. In 1854, Bernhard Riemann developed a geometry of curved spaces as a purely mathematical exercise. He had no physical application in mind. He was generalizing Euclid's geometry to curved surfaces of any number of dimensions. 60 years later, Einstein needed exactly this geometry to describe how mass curves spacetime. Riemann had unknowingly created the mathematical language of gravity. Third, group theory. In the 1830s, a French mathematician named Évariste Galois developed the theory of abstract symmetries to solve problems about polynomial equations. He died in a duel at age 20. His mathematics lived on. 100 years later, physicists discovered that the fundamental forces of nature, electromagnetism, the strong force, the weak force, are described by symmetry groups. The standard model of particle physics is, at its core, a statement about abstract symmetries. 3 times, mathematics developed in pure abstraction, applied to physics decades or centuries later. Each time the fit was exact. Einstein himself, in his 1936 paper Physics and Reality, wrote, "The eternal mystery of the world is its comprehensibility. The fact that it is comprehensible is a miracle. The question isn't whether mathematics works. It does. The question is why." In 1931, a 25-year-old mathematician named Kurt Godel published a proof that changed our understanding of truth itself. His first incompleteness theorem showed that any consistent mathematical system powerful enough to express basic arithmetic will contain true statements that cannot be proved within that system. Not because we haven't tried hard enough, because it's mathematically impossible. His second theorem went further. No consistent mathematical system can prove its own consistency. You cannot use a system to fully validate itself. You always need something outside. What does this mean in plain language? Mathematical truth is larger than mathematical proof. There are things that are true, provably true, that no formal system can demonstrate from within itself. Human mathematicians can recognize these truths. We can see that they're true even though no algorithm can prove them. This led the philosopher John Lucas, and later the Nobel Prize-winning physicist Roger Penrose, to argue that the human mind is not a computer. If we can recognize truths that no algorithm can prove, then our mathematical intuition exceeds computation. This is the Lucas-Penrose argument. It's controversial. Many philosophers reject it, but it raises a genuine question about the nature of human understanding. Godel himself went further still. In his private notes around 1941, he wrote a formal proof of God's existence using modal logic. It circulated privately for decades and was published after his death. In 2013, computer scientists Christoph Benzmuller and Bruno Walzenlogel Paleo fed Godel's argument into automated theorem-proving software. The computer confirmed the argument is logically valid. The conclusion follows from the premises. The computer didn't prove God exists. It proved the argument isn't a logical fallacy. Whether the premises are true remains an open question. Godel was a theist. He believed in God, in the immortality of the soul, and in what he called mathematical Platonism, the view that mathematical objects exist independently of human minds. He told his friend the philosopher Hao Wang, "The world is rational." Godel was not alone. Some of the greatest mathematical minds in history found their work pointing toward something beyond mathematics. Georg Cantor developed the mathematics of infinity in the late 1800s. He showed there are different sizes of infinity. The infinity of real numbers is larger than the infinity of natural numbers, and there's a hierarchy stretching upward. But Cantor believed there was an absolute infinity that transcended all mathematical infinities. He identified it with God. Blaise Pascal invented probability theory in the 1600s, one of the founders of modern mathematics. He is also famous for Pascal's wager, a decision-theoretic argument that, given the infinite stakes involved, belief in God is the rational choice under uncertainty. Leonhard Euler, perhaps the most prolific mathematician who ever lived, was a devout Calvinist. His famous identity, e to the I pi plus 1 equals 0, connects 5 fundamental constants in a single equation. Mathematicians call it the most beautiful equation ever written. And then there was Srinivasa Ramanujan, a self-taught Indian mathematician who produced thousands of formulas, many so extraordinary that professional mathematicians couldn't prove them for decades. Ramanujan attributed his insights to the goddess Namagiri. He said, "An equation for me has no meaning unless it expresses a thought of God." His collaborator at Cambridge, G.H. Hardy, was a committed atheist. Hardy couldn't explain where Ramanujan's insights came from. But he couldn't deny the results. Now, many great mathematicians were atheists. Bertrand Russell, David Hilbert, G.H. Hardy himself. Mathematics doesn't compel theism, but it doesn't compel atheism either. The pattern is simply this: people who spend their lives exploring the deepest structures of abstract thought often find those structures pointing beyond themselves. This brings us to a question that science itself cannot answer. Why do the laws of nature exist at all? Science describes how the universe works. It doesn't explain why there are laws in the first place. Why is the universe ordered rather than chaotic? Why is it comprehensible to human minds? These aren't scientific questions. They're philosophical ones, and they're real. The Scottish philosopher David Hume identified this problem in 1748. We assume the future will resemble the past. We assume the laws of nature are uniform, but we cannot prove this from experience alone. The very reliability of science rests on an assumption that science cannot justify from within itself. This is the problem of induction. It has never been solved. Godel's second incompleteness theorem makes a parallel point. No formal system can prove its own consistency. Apply this to science. Science is extraordinarily powerful within its domain, but it cannot fully validate its own foundations. The Oxford mathematician John Lennox puts it this way: "The more I understand science, the more I believe in God, not because science proves God, but because the mathematical structure of the universe raises questions that science alone cannot answer." Some argue that science will eventually explain everything, but this claim, sometimes called scientism, is itself not a scientific claim. The statement "only science can give us knowledge" is not itself a scientific statement. It cannot be tested in a laboratory. This is the final episode in a 5-part series. We've examined the question of God's existence from 5 independent angles: the universe itself, the fine-tuning of physical constants; consciousness, the hard problem of subjective experience; history, the universal human intuition of a creator appearing independently across civilizations; biology, the information content of DNA, the unsolved origin of life; and now mathematics, the unreasonable effectiveness. Godel's incompleteness, the limits of science. 5 domains, 5 independent lines of evidence. None of them proves God exists. Each of them has counter-arguments that deserve to be taken seriously. Survivorship bias in mathematics, formalism, naturalistic explanations for consciousness and morality, the multiverse as an alternative to fine-tuning. These objections are real, but here's what's striking. The evidence converges. Cosmology, consciousness, history, biology, and mathematics all raise the same question from different directions. Why is there something rather than nothing? Why is that something ordered, comprehensible, and beautiful? No single piece of evidence is conclusive, but the convergence of independent lines of inquiry is itself significant. When 5 different fields point in the same direction, the honest response is not certainty, it's attention. We started this series with a question. Not a thesis, not a sermon, a question. The evidence from 5 independent domains, physics, neuroscience, history, biology, mathematics, converges on something that the greatest minds in each field have wrestled with, something that cannot be easily dismissed. The universe didn't have to be comprehensible. It is. Mathematics didn't have to work. It does. Consciousness didn't have to exist. It does. What it all means is a question each person must answer for themselves. The evidence converges. What it means is up to you.